So we decided to use a big data platform like Hadoop and an RDBMS like MySQL to solve the housing recommendations problem. These are both open source technologies. You probably have Hadoop clusters and MySQL database running on premises. So let's assume that your team already has this recommendation system working on-prem and see how to migrate it from on-premises to Google Cloud Platform. Of course, you want to do that only if the migration can add value. So we will look at that as well. For our housing recommendation model, let's say our data science team already has a working on-premise model using a Spark ML job on your Hadoop cluster. They're interested in the scale and flexibility of GCP, and they want to do a like-for-like migration of their existing Spark ML jobs from on-premises, and they want to do this as a pilot project. As explained in the previous lesson, we can get away with computing predicted ratings once a day. We don't need to compute recommendations in real time. So Hadoop batch processing is enough. Here, we'll use Spark ML, but instead of doing it on premises, we'll run the machine learning job on Cloud Data Proc and store the ratings in an RDBMS in Cloud SQL, because this is a relatively small data set of 5 recommendations for every user. So this is what you will practice in your first lab. Incidentally, this is why the smart reply in Gmail is so amazing. Unlike our housing recommendations, smart replies recommendations have to be done in real time when a new email pops up in your mailbox. Needless to say, Gmail is doing something far more sophisticated than what we're talking about here. Here is how we decided on using Cloud SQL among the other big data products available for storing our ratings. This is a good reference to follow based on your storage access pattern. We'll cover the solutions in your other scenarios in this course, but briefly, use cloud storage as a global file system. Use Cloud SQL as an RDBMS, as a relational database management system, for transactional relational data that you access through SQL. Use data store as a transactional NoSQL object-oriented database. Use Bigtable for high throughput NoSQL append-only data. So not transactions, append-only data. So a typical use case for Bigtable is sensor data for connected devices, for example. Use BigQuery as a SQL data warehouse to power all your analytics needs. So here, we wanted a transactional database, and we expect to have data volumes in the gigabytes or less, and so hence, Cloud SQL. If you're a more visual learner, here is another good map of visualizing where to store your data in GCP. If your data is unstructured, like images or audio, use cloud storage. If your data is structured and you need transactions, use Cloud SQL or Cloud Data Store, depending on whether you want your access pattern to be SQL or NoSQL. And by NoSQL, we mean a key value pair. In other words, you'll be trying to search for data based on a single key, use data store. If you'll be finding data using SQL, use Cloud SQL. Cloud SQL generally plateaus out at a few gigabytes. So if you want a transactional database that is horizontally scalable so that you can deal with data larger than a few gigabytes, or if you need multiple databases, so you want them spread globally, use Cloud Spanner. So another way to say it is, if one database is enough, use Cloud SQL. If you need multiple databases, either because you have a lot of data or because your application needs to be transactional across different continents, use Cloud Spanner. If your data is structured and you want analytics, consider either Bigtable or BigQuery. Use Bigtable if you need real-time, high-throughput applications. Use BigQuery if you want analytics over petabyte-scale datasets. For our housing recommendation use case, we want to store our ratings and predictions somewhere. This is a structured dataset of user ratings and houses. It's built for a transactional workload, writes and reads, and one database is enough for a small dataset, and hence we pick Cloud SQL. So what's Cloud SQL? It's a Google-hosted and managed relational database in the cloud. Cloud SQL supports two open source databases, MySQL and Postgres, and other database solutions. In our case, we'll be using MySQL. One of the advantages of Cloud SQL is that it's familiar. Cloud SQL supports most MySQL statements and functions, even stored procedures, triggers, and views. It brings the benefits of cloud economics in the form of flexible pricing. You can pay for what you use. What do I mean by that? GCP manages the MySQL instance for you. This means things like backup and replication. It's on the cloud, so you can connect to it from anywhere. You can assign it a static IP address, and you can use typical SQL connector libraries. Because it's behind the Google firewall, it's fast. You can place your Cloud SQL instance in the same region as your App Engine or Compute Engine applications and get great bandwidth. Also, you get Google security. Cloud SQL resides in secure Google data centers. So that covers where we'll be storing the recommendations. But how will we compute these recommendations in the first place? Where will we be doing the compute? Let's review where big data computations have been done historically and even today. Before 2006, big data meant big databases. Database design came from a time when storage was relatively cheap and processing was expensive, so it made sense to copy the data from its storage location to the processor to perform data processing, and then the result would be copied back to storage. Around 2006, distributed processing of big data became practical with Hadoop. The idea behind Hadoop is to create a cluster of computers and leverage distributed processing. HDFS, the Hadoop Distributed File System, stored the data on machines in the cluster, and MapReduce provided distributed processing of this data. A whole ecosystem of Hadoop-related software grew up around Hadoop, including Hive, Pig, and Spark. Around 2010, BigQuery was released, which was the first of many big data services developed by Google. Around 2015, Google launched Cloud Dataproc, which provides a managed service for creating Hadoop and Spark clusters and managing data processing workloads. The other piece of our system is a software that runs on Hadoop. The software in this case is to train a machine learning model for creating housing recommendations. In this case, we used Spark ML, which is part of Apache Spark. Apache Spark is an open source software project that provides a high-performance analytics engine for processing batch and streaming data. Spark can be up to 100 times faster than equivalent Hadoop jobs because it leverages in-memory processing. Spark also provides a couple of abstractions for dealing with data, including what are called RDDs, or resilient distributed datasets and data frames. We'll be using our Spark job for the housing rental recommendations. We'll be using our Spark job for the housing rental recommendations, but we'll be doing the computation on Cloud Dataproc.